last unit, we talked a lot about the qualitative characteristics of compounds and the reactions that they will form. So that was all qualitative. Now we're going to get into the quantitative aspects of molecules and atoms, learning about their mass, how to actually count the number of atoms or molecules that we have. And so one thing that in this lesson I'm going to introduce is the concept of using one single word to represent a number. And there actually are a number of examples of this in your everyday life. So let me show you some examples right here. Okay. When I talk about a case of soda, if I'm going to go to the store and buy a case of sodas, you might not have realized this, but that means a specific number. That's 24 cans of soda. If I have a gross of pencils, obviously this applies more for teachers than for students, but if I have a gross of pencils, I have 144 pencils. If I buy a ream of paper, that's not just a random amount of paper. That is exactly 500 sheets of paper. One that you're familiar with, a dozen is 12 eggs, okay? If I say I have a pear, it's implied to be 2. So we have a number of words that represent numbers. So let's actually practice quickly using conversions with these words that represent numbers, okay? And then I'll get into the chemistry of it in just a second, I promise. So the first question, how many dozen nails do 50 nails make up? Well, again, just to get back to our conversion, if I have 50 nails and I want to get into dozen, what I'm going to do is I'm going to put the unit I want to get rid of on bottom, nails, and the unit I want to get into up top. So I'm going to put dozen up top. Okay, and then I'm going to put the relationship. I know that 1 dozen is 12 nails. Okay, so what will that be? Well, I'm going to take 50 and I'm going to divide it by 12, and what I get is 4.1666667. So I tell you not to round based on sig figs. So let's just say, I'm going to say 4.2. Okay, it's fine. I'm not going to grade you on the rounding. It's the concept I care about more right now than rounding. Okay, 4.2 dozen. Okay. So let's look at one more example and then let's get into the chemistry of that. How many cases of soda do I need to buy if I want 130 cans of soda? Okay, well, I'm going to start off. My given is 130 cans. And I want to get into cases. So I'm going to put cans on bottom. And I'm going to put cases up top. Okay. And looking back at our diagram, I know that one case is 24 cans. So in order to determine how many cases I need, I'm going to take 130 and I'm going to divide it by 24, and what I get is 5.4166667. Now, if I'm asking how many cases I need to buy, you can't buy a decimal of a case. So if I have 5.4 cases, in order to get 130 cans, I'm going to actually have to overbuy a little bit. So I'm going to say I need 6 cases. Okay. All right, let's actually see this applied in chemistry now. The way that we apply this is using what is called Avogadro's number. So Avogadro's number tells us that there are 6.02 times 10 to the 23rd, either formula units, molecules, or atoms in 1 mole. Okay? So formula units, when do we use the term formula units? If you notice here, I've got Na plus and Cl minus, so this applies when I have an ionic compound. So if you have an ionic compound, you're going to be talking about 6.02 times 10 to the 23rd formula units. Molecules, that applies when I have a covalent compound. Remember, a nonmetal and another nonmetal. So for example, if I have a mole of water, H2O, I have 6.02 times 10 to the 23rd molecules, right? So Avogadro's number is saying 6.02 times 10 to the 23rd of one of these equals 1 mole. So that is the concept, 1 mole. Mole is the word that represents a number, and the number is 6.02 times 10 to the 23rd. Just like 1 dozen represents 12. And then finally, if you have a single atom all by itself, then you'll refer to it as atoms. Okay? Now, before we get into actually analyzing Avogadro's number and looking at the number of these particles, I really quickly want to make sure that these concepts, that these terms make sense. The reason why we use the word formula unit for an ionic compound and molecule for a covalent compound. Formula units, when you have an ionic compound, you don't just have one individual molecule like you do, for example, for water. They're not floating around. Instead, ionic compounds exist in crystalline structures like what you can see right here. And so when we're talking about a single formula unit, we're talking about one of these, so NaCl, one of those is a formula unit within the entire crystalline structure. And so by saying formula unit, we are noting that it is in a crystalline structure, while a molecule, you can have individual molecules that are floating around separately. So let's practice with this. All right, if I tell you I have 1 mole of Na, how many and what type of particle do I have? Well, I know 1 mole tells me I have 6.02 times 10 to the 23rd. And notice, since it's just an atom all by itself, I'm going to say that I have 6.02 times 10 to the 23rd atoms. Notice how large 6.02 times 10 to the 23rd is. I would have to write 602 and then add 21 zeros after it in order to write it in standard notation, okay? If I tell you I have 1 mole of sodium phosphate, that means I have 6.02 times 10 to the 23rd. Okay. Sodium phosphate, Na, is a metal, so this is going to be an ionic compound. So in this case, I would say I have 6.02 times 10 to the 23rd formula units. Now, you can write this as an abbreviation. If you want to write it as form U, that is fine. Please do not just include the first 2 letters. I don't have to spell it out, but don't please. So form U, or just write out formula units. All right, 1 mole of carbon dioxide would be 6.02 times 10 to the 23rd. Okay. Now carbon dioxide is covalently bound because I have 2 nonmetals. So here I would have 6.02 times 10 to the 23rd molecules. Okay, so let's actually practice with this concept now. So if I have 2.12 moles of C3H8, how many molecules do I have? Well, 2.12 is my given. I'm in moles. Just like what I did before with words that represent numbers that I'm familiar with, I can do this. I can put moles on bottom to get rid of them, and I can put molecules up top. So I'm going to put MOLEC to represent molecules so I don't confuse molecules and moles. Okay? And then according to Avogadro's number, I know 1 mole is 6.02 times 10 to the 23rd molecules. Okay? So when I do this, I'm going to get out my calculator. 2.12 times 6.02 times 10 to the 23rd, and I get, unrounded, 1.27624 times 10 to the 24th. Okay, really quickly, I need to round. 2.12 has 1, 2, 3 sig figs. 6.02 has 1, 2, 3 sig figs. And so 2.12 is going to only have 3 significant figures. 1, 2, 3 for my final answer. So this is going to round to 1.28 times 10 to the 24th. And my units for this are going to be molecules. Okay, and that's all there is to it. It's really not that bad. It's just kind of a weird concept, but just like a dozen means 12 or a pair means 2, a mole is 6.02 times 10 to the 23rd of either atoms, molecules, or formula units. Okay, let's do one more practice problem. I give you 4.65 times 10 to the 24th formula units. That's my given. So I'm going to write this as form U. Okay, and so to get out of form U, because I want to get into moles, I'm going to put formula units on the bottom. and I'm going to put moles up top. Okay, and I know that 1 mole is 6.02 times 10 to the 23rd formula units. So what you need to do in your calculator, and try this right now as I do it, you're going to take 4.65 times 10 to the 24th formula units, okay? And you're going to divide by, make sure that the 6.02 times 10 to the 23rd, make sure that that value is in parentheses since it has a multiplication symbol in it, okay? So I made sure that mine was in parentheses, and the value that I got, unrounded, was 7.724, let's say 3, okay? Let's figure out sig figs. 4.65 has 1, 2, 3 significant figures. 6.02 has 1, 2, 3 significant figures. So my answer needs 3 sig figs. So 1, 2, 3 sig figs. Okay, and so what I'm going to do is round this. It becomes 7.72, and my units are moles. And that's all there is to it.